can be quite confusing. Okay. We will discuss, okay, after I finish this lecture. Okay, we will discuss on that. Okay, just 7 question. I hope I can discuss on the question. Okay, on the pre-recorded video, I have covered at least 4 from these outlines. Okay, subthreshold conductance, channel length modulation, mobility variation, and velocity saturation, and also ballistic transport. So I just want to summarize from here. So subthreshold conduction happens, okay, when so this is your IV characteristic. Okay, the ideal one, as you can see, the ideal one means that you apply the gate voltage. This is for the case of N channel. You apply gate voltage greater than 0, and you also apply if the gate voltage didn't reach the threshold voltage, should be there is no current flow, means that there is no inversion channel created yet. Okay, however, when the VG reach the threshold voltage, and also the VG reach the threshold voltage, okay, then only the inversion channel created, and it will increase. Okay, so this is supposed to be the ideal case. Okay, however, during experimental, this doesn't happen. Okay, so instead of it, before it reach the threshold voltage, there is a slightly current produced over here, as you can see. Okay, until it reach the threshold voltage, then the current will increase linearly. Okay, so what happened here at the curve region here, this is the subthreshold region. Subthreshold region means before the threshold. Okay, before it reached threshold, okay, there is a current created. This is due to the electrons, okay, from the metal, and also due to the initial electrons that being attracted lah, like small number of electrons, say, meaning that there is a small number of current produced, okay, before it reach the threshold voltage. Okay, so this one we call it as a subthreshold region or weak inversion. Okay, I believe that you have listened to the pre-recorded video. So that is subthreshold conduction. Okay, channel length modulation happens when you apply drain voltage. Okay, drain voltage. If you still remember, you apply drain voltage in your lab, microelectronic lab. So 2 types of drain voltage apply. Okay, when you measure the IV characteristic, okay, there are 2 plot that you got, okay, from the simulation. Okay, being plotted 2 plots. Okay, so that 2 plots is actually represent for 2 different drain voltage applied. Okay, I don't know whether you still remember or not. Okay, you got 2 plots, 2 lines, so that is represented for VD, 2 different VD. Okay, one VD 0.05 volt. Okay, that is VD at linear region. Okay, the other one when you apply VD at 1 volt, so that is at saturation region. So both linear region and saturation region. So for the case of saturation region, where you apply VDS greater than the VDS saturation. So in a transistor, it has its own specification sheet. Okay, it has threshold voltage value. Okay, threshold voltage value that is in the specification sheet. Okay, other than that, it also has the value for VDS saturation. Okay, so if you apply VDS greater than the VDS saturation, so this happens. Okay, where pinch off happen. Okay, so this is from the previous lecture, MOSFET operation. So during pinch off occurred, okay, there is a high electric field at the region under the drain. Okay, so meaning that instead of you have a square of channel from source to the drain, okay, the channel region near or underneath the drain will be pinched off. Okay, there is no channel region over here, so we call it as a depletion region or delta L. So this is channel length modulation. Okay, this is what happened in channel length modulation. Okay, if you want to listen again. I will upload the pre-recorded without the question. Okay, you can listen to that again. So just today, I will give you summary. Okay, mobility variation. So mobility means how mobile. So when the electrons is when the channel is created, okay, channel is created. Okay, channel created underneath the oxide. Okay, so the electron starts flowing, okay, from source to the drain. Okay, mobility of electron means how mobile this electron moves, okay, from source to the drain, how fast. Okay, there is a velocity saturation. So the velocity of electron has its limit as well. So the the velocity saturation of electron is 10 to the power of 7 volt per centimeter square, if I'm not mistaken. So that is how mobile. Okay, how mobile. So this mobility or this movement of electron from source to the drain may vary. Okay, means that the mobility may degrade. Okay, may degrade. So what does the effect degrades this mobility? So there are two. Okay, influenced by the gate voltage. Okay, influenced by the gate voltage means that there will be not uniform electric field, okay, distributed along the gate over here. Okay, there will be electric field that over transverse. Okay, so we call it as a transverse electric field. Okay, instead of up to until oxide, there will be transverse electric field that will go further. Okay, sometimes towards the channel, sometimes towards the oxide. So this kind of transverse electric field will give obstacle to the electrons to flow from source to the drain. Okay, there is an obstacle for the electrons. So electron has to avoid this obstacle and go straight again, and so on. So the electron, instead of moving straight, okay, from source to the drain, now it has obstacles, so it has to move sort of like zigzagging movement. Okay, so this mobility vary due to this effect. Okay, other than that, because of that, okay, so what effect usually called is the surface scattering effect. Okay, so these are due to the transverse electric field. Okay, and the surface may not as smooth. Okay, flow. There is a collision or obstacle. So this we call it as the surface scattering. Okay, where surface scattering may degrade the mobility of electron from source to the drain. Okay. All right, so this is just a summary, okay? And then ballistic transport. So ballistic transport means ballistic transport only occurred in the short channel. Okay, in the short channel. In long channel, drift diffusion transport means that the electron randomly distributed, okay, in the channel, flow from source to the drain. Okay, ballistic transport where source and drain is very near. Okay, ballistic transport only occurred in short channel. Okay, electron can flow from source to the drain very fast without obstacle, and sometimes in a straight line lah. All right, okay, so today we will continue, okay, for the topic of MOSFET scaling, okay, and also small device geometries, okay, which we will cover on the short channel effect, narrow width effect, and also summary. Okay, all right, so I think for those who do your FYP that regarding to this topic, okay, scale down the transistor gate length and so on. So this will be beneficial lah for you, okay, in understanding what is short channel effect. Okay, although that you have already learn from the lab, okay, but still this will be more on the fundamental explanation. Okay, so let's see. Okay, later we will discuss on the question, yesterday's question. Okay, so let me. All right. Okay. All right. Okay. Can you see my screen?
Yes, ma'am.
All right. Okay. 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 All right. Okay. So for the MOSFET scaling, okay. Okay, so frequency response of a MOSFET can be affected, can be improved by reducing the channel length. Okay, so in the MOSFET operation topic, okay, we have seen on the frequency response, okay, at low frequency and high frequency. So those behave differently, especially for the capacitance versus voltage characteristic. Okay, those are difference. Okay, behavior at low frequency and high frequency. Okay. Okay, so this frequency response can be improved, okay, by reducing the channel length. Okay, so what are other parameters that need to be scaled as the channel length scale down? Okay, so there is a constant field effect scaling and also generalized scaling. So what is this? So how the channel length is being scaled? Okay, so to what parameter? So what is constant field scaling? Okay, so constant field scaling means the device parameter or the physical dimension and voltage. Okay, so device parameter means includes the physical dimension. So physical dimension for those who do FYP in microelectronics or on the device structure. So physical dimensions, okay, means it's W, the width. Okay, that is physical dimension. You know the value. How much? 1 micrometer, 10 micrometer. So that is the physical dimension. L, channel length, also physical dimension. Okay, concentration, Na, Nd, those are also physical concentration. Okay, other than that, and so on. Okay, there are a lot. Tox, okay, oxide thickness. So that is also physical dimension where you can see the you can see it, okay, the parameter, and also you can know, okay, the length, okay, how much the figure, and also the voltage, okay, how much we apply the voltage to the gate, okay, VGS, and how much we apply voltage to the drain, VDS. So those these parameter um is actually being scaled. Okay, being scaled means to what parameter? Okay, to what parameter? So one of parameter introduced in constant field scaling is K parameter. Okay, K parameter. Uh, so this parameter introduce K parameter. Although that you multiply all these parameter, for example, to the K value, okay, to the K value. However, when you multiply this to the in constant field scaling, okay, so the electric field must remain constant. Okay, whatever you apply the value or the device parameter to the K value, we have to make sure the electric field remain constant. Okay. Electric field should not be increased or decreased, okay, to ensure the reliability of the MOSFET. Okay, all right. So for example, okay, you have this, your left figure is the original NMOS, okay, original NMOS with L parameter, okay, and also TOX device parameter, and also doping concentration, okay, not to forget, not only the physical dimension, the voltage also VG and VD. So you also have W, okay, width at the back. So this is the width of your transistor. So constant field scaling means that you multiply all these device parameter, the physical dimension as well as the voltage with K parameter. Okay, for example, here you can see now the physical parameter like K, channel length, KL, gate length, you multiply by K. Okay, and the T aux also you multiply by K. Okay, and this is the radius of the drain. Okay, drain region, H region. So RG also multiply by K, and the voltage also multiply by K. If you have W over here, also multiply by the K value. Okay, the concentration also being multiplied by K value. However, it will be multiplied by 1 over K. Okay, so this K scaling parameter, okay, typically the value is 0.7 volt. Okay, 0.7 volt. Right. So and notice that when the channel length is reduced to 0.7 L, okay, the oxide thickness also reduced by 0.7 Tox. Okay, but the doping concentration is must be times by 1 over K, which is 1 over 0.7. So this happened when we use constant field scaling. Okay, so constant field scaling here is the K parameter. Okay, in any specification sheet, so usually they will multiply the values with the K value, and they stated already there the K value is 0.7. So the actual length, so for example, length is given 1 micro. So actual length you has to multiply by K. So 0.7 times 1 micrometer. Therefore, the actual length is 0.7 micrometer. So that is how they do it lah. Okay, and also the concentration, the voltage, and so on. Okay, so the original saturation current is given by this equation. Okay, I know that you already familiar with it. Okay, original current. So current characteristic. Okay, the trend is like this. So you have VGS, okay, and also you have ID. So more on what we call it as a square trend. Okay, so W over L times VGS minus BT square, right? So scale means you have to multiply by the K value, as you can see from here. So all these are multiplied by K, and this multiplied by K. This also multiplied by K. So this one, K for W, okay, times this one K is K square. Okay, over KT ox is K times KL, K. So if you cancel out all the K, so the remaining equation will be that ID scale, okay, this one is equal to K times ID original. So this is the final equation for the ID scale. Okay, so meaning that you have to multiply by the K value, which is K, typically the value is 0.7. All right. So what are the first for the threshold voltage? Okay, for the threshold voltage, in this case, ID scale, you have to multiply by K, 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 and K. Okay. However, for the threshold voltage, K, it didn't affected so much by the K value. Okay, because all the parameter here is equal to the V flat band, the phi FP, and C aux, and just NA. So NA will be like 1 over K. So the threshold voltage didn't affected much by the K value. So the threshold voltage equation will remain the same as the original equation. So it is just like this. I mean that you don't have, so for this one, ID scale, you have to multiply by all the K value and so on. However, for the threshold voltage, no, it will be still remain the same equation. All right. Okay, so this table 11.1 shows the summary of the constant field scaling. Okay, in this table I listed out the scaling parameter and also the device parameter. So the device dimension like L, T, ox, W, and XJ usually multiplied by K. However, the concentration will be multiplied by 1 over K, and so on lah. So there will be and the voltages will be multiplied by K. Okay, the electric field carrier velocity will not be multiplied by K, but it has to be remain the same. Okay, to make sure its reliability won't be degraded. All right. So other than that is the generalized scaling. Okay, generalized scaling is most commonly used lah. Okay, nowadays. Okay, if you still remember, generalized scaling is something to do with the short channel effect and also the narrow width effect. Okay, there are shortcomings. Okay, it means that the limitation in the constant scaling approach just now. Okay, in actual technology or in actual CMOS technology now, okay, voltage is not reduced with the scaling factor. Okay, means that with the K factor, okay, due to several reasons. Okay, one of the reason is reluctance to change the standardized power supply. Okay, usually we won't be multiplied by K value because um, reduce means, okay, if you have voltage, you multiply by kV. So K is 0.7. So usually the value will be reduced, okay, reduced. So we don't want this to happen. Okay, why we don't want to reduce the voltage? Because we don't want to reduce the power, okay, the power consumption or the power supply, and where the CMOS technology already has standardized power supply. Okay, therefore we don't want to reduce that. Okay, so this is one of the shortcomings for the constant field scaling. Okay, then other than that, other parameters like threshold voltage it's not being scaled. Okay, like I've shown you, the VT equation just now is not being scaled, and also the subthreshold current. Okay, which means that ID before VT also not being scaled. Okay, the electric field cannot be maintained. Okay, if we want to use constant scaling, okay, electric field has to be maintained. However, this is hard to maintain. Okay, for long channel, okay, for short channel, it is not really suitable. Okay, where electric field cannot be remain the same or constant. Okay, it may increase. Okay, this electric field may increase if we used this constant field scaling approach. Okay, there is one more approach which is generalized scaling. Okay, so in this generalized scaling, not all parameters are scaled using one scaling factor. Okay, meaning that in constant field, all being scaled by the scaling factor K. K means that all parameter like device dimension, the voltage, being scaled by one scaling parameter. However, in generalized scaling, not like that. Okay, not like that such approach. Okay, parameters such as apply voltage, threshold voltage are scaled more gradually compared to feature sizes L and W. So how it works? So let's see. Okay. So threshold voltage modification. Okay, there are two effects. Okay. One is short channel effect when the L is reduced. Okay. The other one is narrow width effect when the W is reduced. Okay. So this is your structure. So now we want to see this effect. Okay. We want to see this effect. So for example, you have this one. This is your T-aux. Okay. Okay, this is your source and drain. Okay, this is your gate. Okay, so the distance between this is L. So when L is reduced, so for example, when you have 90 nanometer gate length, and then you want to design it with the 60 nanometer gate length. Okay, all the characteristic may change, okay, due to this short channel effect. Okay. What are the effects? So there are a lot of effects. Okay. One of it is the threshold voltage roll off. Okay. One of it, the on current may reduce. Okay. And also the off current or the leakage current may also increase. And other than that, the subthreshold swing may also be affected. So these are the short channel effect. Okay. Other than that, the most important effect here is the drain induced barrier lowering may also be affected due to the short channel. Okay. So this is short channel effect. Okay. The effect of when you reduce the gate length. Okay. Other than that, okay, you also have a parameter like W. So this width. Okay, when you reduce the length, means that the size of your transistor. So we are not focusing on the L. Okay, the length of the gate. Okay, the gate length or the channel length are usually the same. Okay, we also concern on the width of your transistor. Okay, it can be tebal or nipis, so that may be affected as well. Okay, so when you reduce the width, okay, means that the width become narrow or smaller. Okay, there will be an effect. So we call it as a narrow channel effect. Okay, narrow channel effect or narrow width effect are the same. Okay, some book use narrow channel effect, some book use narrow width effect. Okay, it is the same. So when all these two reduce, okay, usually there will be an effect after that. So what is the common effect do occurred here? So let's see, usually on the threshold voltage, threshold voltage. Okay, we will see the effect of gate length and also width, okay, towards the threshold voltage. Okay, all right. So in short channel effect, okay, the left figure here, I think you familiar already. So the left figure is the cross section of the long channel and channel MOSFET. Okay, as you can see from here. So the region over here is L. Okay, so this is at flat band. Okay, meaning that no channel. Okay, no channel created yet, and so on. Okay, and this one still this is at inversion. Okay, for both the top figure is for the long channel. Okay, the bottom figure is for the short channel. All right. Okay, for this one. So for the long channel, the length, okay, between source and drain is given by L. Okay, as you can see, when you apply at inversion, of course, when you apply VG greater than the threshold voltage, okay, then the channel will be created over here. All right, the channel will be created, and there will be inside this channel, of course, there is a charge. Okay, the charge also, number of charge or due to the XDT is increased lah. So XDT increase, there will be XDT, and also inside the XDT or the space charge region, there will be a charge. Okay, this is the electron charge, for example, for this N channel. Okay, for the short channel, okay, for the short channel, the L now reduced. Okay, the L now reduced. Okay, however, during inversion, you still apply VG greater than the threshold voltage. Okay, and there will be an electron. There will be, there will be um, a charge. Okay, or the XDT also will be created. Okay, however, the charge now reduced. Okay, the charge now reduced because the area of the XDT for short channel is also reducing. Okay, so this is what happened at inversion for short channel length. Okay, however, the depletion region created. Okay, and still the charge also will be created, okay, due to the channel created underneath the oxide. Okay, however, the what we call it, the volume of charge Qn now is smaller compared to the long channel. All right, so due to this, okay, now the space charge region become compact. So this is, oh, sorry, eh, wait, okay. So this region now become compact, okay, due to the difference area, okay, of the space charge region, okay, due to this area is larger and this area is smaller. Okay, this area is smaller. Therefore, the threshold voltage for long channel and short channel will be different. Okay, will be affected. Okay, due to the short channel. All right. So let's see how it affect the threshold voltage. Okay, particularly is due to this charge lah. Okay, due to this charge. Okay, because the area now reduced, okay, for the short channel, and also the charge also reduced. Okay, we know that the equation for threshold voltage, okay, depends on the Q. Okay, Q, if you still remember. Okay, let's see. All right, so this is what happened. Okay, oh, sorry. Okay. Okay, so for long channel, okay, for long channel, this is the equation. You all have with it. We have seen this equation and used this equation in the tutorial and also in the example. So the threshold voltage equal to the QSD. If you still remember, QSD, okay, QSD is equal to E N A X dt, okay, where the Q is the total charge inside this X dt. All right, so when this X dt reduce the area, so the charge also reduce. So like I said, so the threshold voltage depends on the charge, okay, the charge, okay. So space charge region depth is XS. Okay, so this is the region XS. Okay, and also you also have space charge region depth at drain. Okay, this in Neyman said, so this space charge region under the source and also under the drain is equivalent under the channel. So this one all equivalent, and it is given by x dt. Okay, and the charge per unit area, okay, under the gate now is a little bit different. Okay, in short, in long channel, okay, in long channel, as you can see, it is like a square lah, square. Okay, very straightforward. Okay, the area is in square. However, okay, if we consider the source and everything, there will be space charge region under the drain. There will be a space charge region under the source, and there will be also uh, edge area over here, which is represented by R. Now, instead of the region area is square or rectangle for the long channel, so in short channel, now it become like a trapezoidal area. Okay, trapezoidal area. Okay, so this area will be changed now. Okay, this is for the case of short channel. Okay, for the short channel. So this area now is being no more like a rectangle, so it has a new area. Okay, so area of trapezoidal is equal to, okay, so in Neyman they just wrote like that. Okay, so this area is trapezoidal is L. Okay, so this region is, so this length is L. Okay, this length is L, right? Okay, so this is L. Okay, plus with the new L over here, new L. So this is L prime. Okay, over 2. Okay, over 2. So this is trapezoidal area. So L plus L prime over 2. So that's why the charge per unit area, instead you have E and A x dt over here, you have to multiply with the new area, which is L plus L prime over 2. Okay, from the geometry side, they actually simplify the equation or derive the equation like this. Okay, you can look at the Niemann if you want to know further. So L plus L prime over 2L is given by this equation, where they consider the R, which is the depth under the drain. Okay, and also this R, and finally the charge is given by this portion, the long portion over here, E and AXT, not a straightforward E and AXTT. So now the charge has to multiply with the geometry or the area geometry of the trapezoidal 1 over R1 minus RG over L, and so on. Okay, so this is the basically the charge lah. All right, so you can see that. So what is I'm trying to explain here, okay, when you reduce the channel length, okay, when you reduce channel length, the behavior is the same. Okay, however, the channel area under of the short channel become reduced. Okay, the total charge also reduced. Therefore, the threshold voltage can no longer apply by this threshold voltage. For short channel, we cannot use this. Oh, okay, we cannot use this equation for short channel. Cannot. Okay, so for threshold voltage, equation will be much more complex for short channel, where it has to consider the geometry parameter. Okay, so what you did in the simulator, like Centaurus, okay, behind the scene, behind the simulator, there is an equation model. So basically, the simulator run the equation model. So it has its equation where they have to consider a lot of parameter. So when it comes to the short channel, a lot of things need to be considered. Okay, the parameter, the geometry parameter, and then the quantum effect, and so on. So these, okay, may this is actually coming from the complex equation. Okay, so for short channel, it is straightforward. So this equation for short channel. Okay, however, for for long channel, it is straightforward. Okay, what we have seen from the previous lecture and so on. But for short channel, all become complex. Okay, we have to consider a lot of things. Okay, in the equation. So the equation also become complex. Okay. All right, so not only the equation become complex, there will be change, okay, for the threshold voltage, okay, in long channel and also short channel. All right, so for the threshold voltage equation, okay, basically you have to the change means that the delta VT so short channel for VT for short channel minus VT for long channel given by this equation. Okay, and finally you will have the delta VT is given by this complex equation. Okay, so this is just maybe up to 90 nanometer. Okay, so for this case, when the channel length decrease, okay, the threshold voltage shift in the negative direction, means towards the depletion mode, means that the threshold voltage will shift to the left. Okay, when the channel length is decreased. Okay, so this is the example. Okay, for this example 3, I think this very straightforward lah, because just want to apply this long equation. Okay, for the threshold voltage shift. All right, so calculate the threshold voltage shift VT delta VT. Okay, due to the short channel effect. Okay, consider the N channel MOSFET concentration Na 3 times 10 to the power of 16 and L 1 micrometer, Rg 0.3 micrometer, Tox 20 nanometer. So Tox given, Cox given by EOX. So this is EOX, EOX, okay, over Tox 3.9 times 10, 8.85 times 10 to the power 14 over 200 times 10 to the power of 8, okay, equals to 0.726 times 10 to the power of minus 7, okay, phi FP, VT ln NA over NI. So NA is 3 times 10 to the power of 16. Ni for silicon. Okay, Ni for silicon, make sure you use the correct value. It is 1.5 times 10 to the power of 10. But if the question is germanium, use this. Okay, cannot use that. Okay, you have to use for germanium intrinsic concentration. So 5Fp 0.3758. Okay, of course you want to use XDT. Okay, find the XDT over here. So plug in all the value. You should get 0.18 times 10 to the power of minus 4 centimeter. Okay, finally, you plug in the equation, the long equation that is approximate to the RJ value also given. So finally, delta VT is equal to negative delta BT here means that VT short channel, okay, VT short, okay, minus VT long channel, okay, equal to negative 0.0726 volt. Okay, this is straightforward lah. Okay, where you just plug in all the parameter in the equation, then you will get it. Okay, so the threshold voltage change now. Let's see. Okay, from here. So left figures is the threshold voltage versus channel length, okay, for various substrate dopings, okay, for various substrate doping. As you can see, this is the threshold voltage, okay, and this is the channel length, okay, channel length. All right, as you can see, for different concentration, okay, uh, 10 to the power of 15, 10 to the power of 16, and 10 to the power of 17. All right, as you can see, the V means the threshold voltage, okay, threshold voltage for the gate length from 6 nanometer to 2 nanometer as micrometer. So the gate length, the threshold voltage is not much affected. Okay, not much affected. Okay, for low doping, not much affected. Like meaning that the threshold voltage like almost the same lah. For 6 micrometer, when you downscale to 2 micrometer, uh, still the same. For 10 to the power of 16, okay, until 2 micrometer also almost the same, okay, basically. So if you can see from here, okay, if you can see from here, but when you have like increase channel doping at heavily dope, okay, so this is like heavily dope, okay, heavily dope, okay, uh like I said, the concentration is instead of straight line, so there is a decrement lah, a little bit. Like I said, not only the threshold voltage not only depends on the gate length and so on, it depends a lot of things, concentration, sometimes oxide thickness do affect lah. But now we just want to see on the effect on the gate length. Okay, if you can see here, okay, for L less than 2 micrometer, okay, the effect now become more severe. Okay, so the channel length reduced, okay, less than 2 micrometer. The characteristic now has of the threshold voltage now is reduced this much. Okay, as the cause heavily dope, it reduced much more affected, and for the higher heavily dope also it much affected. So we can see from here that we can assume that short channel occurred when L less than 2 micrometer. Okay, we didn't say that 3 micrometer is a short channel yet. Okay, but when L less than 2 micrometer, so this experimental shown in Neiman, it shows that it short channel effect occurred. Okay, when L less than 2 micrometer. Same goes to this. Okay, the right figure is actually the same thing. However, now they vary the voltage lah, the voltage. Okay, now here we just look at the left figure. We just look at the case for doping, length, and also threshold voltage. However, the right side, they look on the when they apply different voltage at the VDS, okay, but still this still the same. This is the threshold voltage, okay. this is channel length. As you can see, the channel length reduced, okay, but with the different application of voltage, okay, it also affected like this lah, okay, like this. So this is for no voltage apply, means that normal, okay, same like the left one. However, it do affect also the performance with the voltage, okay, voltage difference, the performance also difference. All right, so narrow width effect, okay, narrow width effect also affected, okay, when we have narrow W, okay, this is the this is the front value, front view, okay, with the L view, okay. This is the side view with the W view lah, where you can see the width view, okay. So L is to the back, okay. So here, not at narrow width, okay. Of course, the region also, okay, the region also be affected over here, okay, and it also has this portion area, okay, this portion of area which is represent as the delta QB, okay, and this also represent as delta QB. All right, okay. So charge per unit area under gate, okay, when narrow channel effect occurred, so QB equal to the QB naught plus delta QB. Okay, now QB, instead of you have E and AXDT, you have to multiply with the WL. So this is the equation. Okay, finally, okay, this is more complex. Okay, we're not going to look or apply this, okay, in this topic. However, I just want to show you. So this is what happened for narrow channel effect. Do also affect the performance of the threshold voltage, because now it has a fitting parameter for W. Okay, for W for width. Okay, now the threshold voltage change is becoming this equation, where it has to multiply the parameter, what we call it, I don't know, this term. Okay, so this is actually represent the scaling parameter for width. Okay, so the equation now much more complex. Okay, however, let's see the effect of gate width on the threshold voltage. Okay, as you can see, this is the threshold voltage. So this is the width W, okay, the X one. For different concentration, 10 to the power of 16, 10 to the power of 16, 10 to the power of 16. As you can see, it is remain the same, okay, until what we can see from here, 8 micrometer remain the same. The threshold voltage is remain the same from 20 micrometer to 8 micrometer. Okay, the threshold voltage is remain the same at all concentration. Okay, however, it become more severe, okay, when W less than 8 micrometer. So the characteristic now, the threshold voltage now is affected, become increase, okay, become increase like this. So we can conclude that the threshold voltage, okay, when we reduce the width, okay, the W is reduced, okay, the threshold voltage is increased. Okay, however, for this case, when L is reduced, okay, the threshold voltage is also reduced. Okay, for the case of W, okay, for the case of W, when W is decreased, however, the VTH is increased. Okay, so this is what happened, where you can explain in terms of the area, okay, the channel lah. So this is what happened. It is to become apparent, okay, and to the suite. Special suite mean for W reduce. Okay. Okay, so this is the summary, okay, with the channel length and also with the channel width, okay, as you can see from here, when L is reduced, Okay, the VT also reduced. However, vice versa for the W. When W is reduced, VT is increased. Okay, so it has two different characteristics for both. Okay, the narrow channel device produces larger threshold voltage. However, for short channel device produces smaller threshold voltage. So this is the summary from yesterday. Okay, subthreshold conduction means that the ID equal to zero, not equal to zero, even when the VGS less than VT. So this mode we call it as a weak inversion mode. Okay, so when L effective reduce, VD increase. So this we call it as during pinch off. Okay, so during pinch off, there will be an effect. We call it a channel length modulation effect. Okay, and the mobility of carrier means that how fast the electron move. Okay, in the channel. So this may be it is not constant. Okay, it may degrade the performance. Okay, the mobility performance. Okay, due to the VGS apply and also the electric field. Okay, the electric field. And the surface scattering effect, okay, increase leads to degradation in mobility. Okay, when L is reduced, the lateral effect also increase, so the carrier flowing through the channel may reach the saturation velocity. Other than that, the tendency in MOSFET design is become smaller. So the principle of constant speed scaling effect has been discussed. Okay, and also the modification in threshold voltage as the device dimension shrink has been discussed as well in terms of W and also in terms of L and also in terms of W. All right. So we've done the lecture. Okay, before I want to discuss yesterday's question activity, do you have any question regarding this lecture? Are you all still there?
Yes.